Today's session will be split into two main parts. The first will deal with the Smith chart basics and principles, and the other one will discuss the basic techniques that used in order to match any RF circuit to the characteristic impedance at its terminal. Okay, so let's now start by looking at the general case of a system that is connected to a transmission line with a characteristic impedance of ZO. When we look at the Smith chart, the ZO impedance is the center point of the Smith chart, like is presented here. In case the system is a shunt, then we would measure zero impedance. The zero impedance is located on the left side of the Smith chart here. The infinite impedance, as if we had an open circuit for our system, then the open circuit is located on the right side of the Smith chart. Okay, the next thing we have to discuss here is the circles here. The circles represent the real part of the input impedance. One word before we continue, we always discuss a normalized impedance. We never discuss the real impedance, and before we do anything on a Smith chart, we have to normalize the input impedance to ZO. We do that by dividing both the real and the imaginary part in ZO. As you can see, if we are on the left side, if the circles are greater than the circle that crosses the center of the Smith chart, then the real part of the impedance is lower than ZO. And if we are inside the circle that crosses the center of the Smith chart, then we have a real part of the impedance, which is actually the resistance. We have a resistance which is greater than ZO. The next thing is the arcs. The arcs on the Smith chart represent the imaginary part of the input impedance. The upper half of the Smith chart represent an inductive reactance to the input impedance, and the lower part, the lower arcs, represent a conductive reactance to the input impedance. As you can see here, the lower arc are represented by minus sign, while the upper arcs represent by plus sign. Now let's look at the example here of an input impedance of 25 plus J25 ohm. When we normalize this impedance, we will get half plus J half ohm, and it is located on the half circle and the half arc. Now, what will happen now if we look at the circle that its center is located on the Smith chart center, and its circumference crosses the impedance that we have just marked. The radius of this circle is the magnitude of the reflection coefficient rho. The formula here is presented, and you can see, and this circle actually has a great significance. If we add a transmission line in the terminal of the system, and we measure the impedance of the system after this transmission line, then we will see that this impedance is rotating clockwise along this dashed line that we have just marked. And let's look now at the same impedance, and we will see that after 1/8 of wavelength, we have accomplished 90 degrees of movement along the circle. And after additional eighth wavelength, which means quarter wavelength of transmission lines, we actually jump to the other side of the circle, the dashed circle, as presented here, as you can see. Up until now, we have discussed the impedance Smith chart, but actually there is another chart which is a little less popular, but is very, very important to matching RF circuits, RF systems, which is the admittance chart. If we look at the admittance chart, then we can see this is actually a mirror image of the impedance chart. This is the same chart with the circles and arcs as before. If we take an example of our system that we have as the same as we did before, we have now a system that its input admittance is 0.02 plus J 0.02 mho. If we look at the circles here, then in this case, the circles represent the conductance instead of the resistance as in the impedance chart. The arcs in this case represent the susceptance, which is the imaginary part of the admittance. If we travel around the center of the Smith chart, this is the same as before as we connected a transmission line in the terminals of our system. The same movement clockwise along this dashed line will be measured if we add a transmission line, and as long as these transmission lines become, the more movement we will do along the dashed line with our admittance that is marked here. Again, we have to remember that the admittance chart is normalized. Here it is normalized to YO. YO is 1 divided by ZO. Now, when we do matching, the most convenient way that I recommend is to put those two charts one upon the other. There are also other ways to use only the impedance chart, but we don't have to work too hard. The easiest way is just to put an overlay of the impedance chart over the admittance chart, and as you can see here, the blue lines represent the admittance chart, and the black lines represent the impedance chart, and when we do matching we will use them both. Now we start the second part of our session by discussing how lumped elements, basic elements, LC elements, and transmission lines influences the input impedance of any system. Now let's take a general case when we have a load with the general impedance of Z load, as marked here. And we add on its terminals a parallel inductor, and then we try to figure out what would be the input impedance of the system and the inductor together. Now, let's look how what happened to the impedance on the Smith chart in this case. Look here. We have the input impedance located here, the load impedance located on the Smith chart here, and then what actually the inductor do? The inductor, since it is parallel, we are adding the susceptance of it to the susceptance of our load. If we want to add a susceptance, then we have to maintain the inductance, because the inductance doesn't change, but the susceptance does change. So we are actually maintaining the circles that we are standing on, but we are changing the arc that we are standing on. Actually, we are moving counterclockwise on the inductance circle that we were on, and we change the susceptance value of the input impedance by this movement. You see again that the movement is along the inductance circle and counterclockwise in this case, because when we add an inductor, of course, the susceptance of our load will be increased. In this case, we see how the movement is toward increasing the value of the susceptance. What is the connection between the value of the inductor and between the change in the location of the impedance on our Smith chart, the Z load impedance? If we look at the initial point and the end point, then we will be able to calculate the difference in the susceptance. This difference is equal to the susceptance of a parallel inductor, as you can see here in this formula. Since in this case we have moved from J1 to J2, then the value of the inductor here is obviously ZO divided by omega. Well, let's now look at the similar case to the case that we have looked at previously. And in this case, we have switched the inductor with a capacitor. Same here, the load is on the right side. Then we added a capacitor in parallel to it, and we measured the input impedance of the load, including the capacitor. What we will see. The blue point represents the load. Then, since we are dealing here again with the capacitor that has only an imaginary part, it contributes a zero to the inductance but influences only the susceptance. Since it influences the susceptance in difference from the inductor that we have discussed before, the movement along the inductance line that remains the same will be clockwise rather than counterclockwise as we have seen before. In this case, the change between the start point to the end point is J 0.75, as you can see here. And this is actually the susceptance that has been contributed by this capacitor. And susceptance of the capacitor is given by J omega C. Then, if we are playing a little bit with the formula here of this specific case, we will get that the capacitor is equal to 0.75 divided by omega ZO. Well, up until now we have discussed cases where the components are in parallel to the load. When we did that, it was more convenient for us to discuss the susceptance and the inductance, because the components in parallel, it's much more easy to view the admittance rather than the impedance. But in this case, we have added an inductor in serial to our load. In this case, it will be much more easy to discuss the impedance. And of course, the impedance is divided to resistance and reactance. The resistance are the circles and the reactance are the arcs, as we have seen before. When we add an inductor, as we have previously discussed, we do nothing to the resistive part of our impedance, because the resistive part of an inductor obviously is zero. Actually, we only change the reactance. So, if this is the case, the movement will be always along the resistive circle that maintains the resistivity of the load, the original load. You can see here when we start from the blue line and we go along the circle that indicates the resistivity of the load. And since we add an inductor, we are going clockwise along this circle, clockwise. And if we look at the value, what is the connection between the movement that we did on a Smith chart to the value of the inductor, then the difference between the end reactance and the initial reactance is, in this case, 0.75 J, is equal to j omega L, obviously. And if we are playing a bit with this formula, we will receive the value of L. In this example, it is 0.75 ZO divided by omega. Now, the broader case of the previous case is a serial capacitor. Serial capacitor, of course, like before, doesn't change the resistive part of the load impedance. It only contributes a reactance to this impedance, and then the Z in comparing to the Z load will have only difference in the reactance. But in difference than before we moved clockwise, but in this case we move counterclockwise along the resistive circle that is equal to the resistive part of the impedance of the original Z load. Now, if we are measuring the difference between the reactance of the endpoint and the initial point, then it will be equal to minus J divided by omega C, which is the reactance of the capacitor. Again, playing a little bit, and we will get that in this case, since the difference between the initial point and the end point is half, 0.5, then the end result, or the end value of the capacitor in this case, is equal to 1 divided by 0.5 omega ZO. Now, the last and very important element that we have to discuss before we move to matching techniques is the transmission line. We have seen previously that if we add a transmission line to a system, in this case we have a load, the Z load, and we add a transmission line with the characteristic impedance of ZO, and then we measure the input impedance of our system, we have seen that the Smith chart view will rotate clockwise along a circle that is marked here in dashed line, that its center is located on the center of the Smith chart, and its circumference crosses the blue point of that represent the impedance. Now, there are a few things that I want to emphasize here. Actually, the transmission line, why we are discussing all these elements. Those elements are actually techniques of changing the location of the impedance on a Smith chart. The end target that we have is to take our impedance that is not matched, it's not the ZO or the characteristic impedance of our system, and we want to change it to BZO. We want to move it from the location that it is located initially and to put it in the center of the Smith chart. The inductor, the parallel inductor and the parallel capacitor and the serial capacitor in inductors, and also the transmission line is a technique of changing the location of the impedance on the Smith chart. Then, by combining those methods, we will be able to take any impedance that's located anywhere in the Smith chart and to put it in the center, which means that our system is matched. Now, in this case, we see that the contribution of a transmission line to the input impedance is only on the phase. If you look at the formula, you can see that the Z load is only added by a phase, E minus J omega L. L is the length of the transmission line. One last thing that I want to emphasize is that we always selected components that are totally reactive, because we don't want to add loss to our system. We don't want to pay in the loss of power or energy when we do a matching. Reactive components, at least theoretically, are lossless. And we have worked with an inductor and a capacitor and a transmission line. If we choose the components wisely, or if we choose the substrate or the transmission lines wisely, then the loss on this component that do the match of our system will be very small, relatively, for instance, for an attenuator. If we use an attenuator, of course we will do a matching, but we will pay a lot of energy and we will lose a lot of energy on this attenuator.